Hello everyone, and welcome to the fifth session of this lecture series entitled EXO in Structural Engineering. In the previous session, we defined our output parameters down to the parameter C, which we named as C of A in EXO, as the letter C on its own is reserved for column. And today we will continue defining the rest of our output parameters. The following highlighted output parameters are all used to determine the level of ductility of the cross-section. As can be seen from the figure on screen, the section can be in the tension-controlled zone, the transition zone, or the compression-controlled zone. Only tension-controlled cross-sections are admissible according to the code, and therefore we need to determine whether the section is adequate or not before we can calculate the design strength. As I mentioned in an earlier session, we can either use C over dt to measure the ductility of the cross-section, or we can use the strain in the steel layer farthest from the neutral axis, epsilon t, to do the same thing. Note that the value of C over dt decreases in the direction of the arrow pointed out on screen, while epsilon t increases in the direction of the same arrow. The ductility parameter of the cross-section that we are studying should be compared with the ductility limits stated by the code in order to decide whether the section is adequate or not. Epsilon t can be obtained using similar triangles from the linear strain distribution shown on screen here, which is one of the Bernoulli beam assumptions. Next, we will determine the value of the output parameter phi, which is done using nested if statements. If the section is compression controlled, then phi is equal to 0.65 and the section is rejected. If the section is in the transition zone, then there is an equation for phi, yet the section is rejected. But I always advise to calculate the value of phi for comparison purposes and in order to figure out if the section at hand can be modified and brought to the tension controlled zone or not. Lastly, if the section is in the tension controlled zone, then phi is equal to 0.9 and the section is accepted. These are the three statements here that will decide the value of phi. If the first if statement is satisfied, then phi is equal to 0.9. If the second if statement is satisfied, then there is an equation to determine the value of phi, and if neither the first nor the second if statements are satisfied, then the last if statement, which is implicit and only the result of which is shown here, which is 0.65, means that if the first if statement is not satisfied and the second if statement is not satisfied, then the value of phi should be taken as 0.65. We will now use three things to determine whether the nominal strength of the cross-section Mn and the design strength of the cross-section phi times Mn are to be calculated or not, depending on whether the section satisfies the code requirements or not. Number 1 is the value of phi, where phi should be equal to 0.9 for the cross-section to be admissible by the code. Number 2, the width of the cross-section B should be greater than or equal to B minimum, which can be translated as the adequacy of the cross-section to encompass the amount of steel in the layer farthest from the neutral axis. as this layer holds the largest number of bars for an efficient distribution of steel in the cross-section. Number 3, the total area of steel reinforcement provided should be greater than the minimum required by the code, greater than or at least equal. We will use nested if statements to check whether these 3 conditions are satisfied or not. If satisfied, then the nominal and design strengths will be calculated. Otherwise, the section will be declared as inadequate and the design strength will not be provided for a section that fails to satisfy the conditions of the governing code. Next, we will introduce the round function to our formulas. The round function is used to specify the number of decimal digits to present for each of the output parameters. The syntax for the round function is the word round followed by parentheses. Inside the parentheses, we have the formula that we want to write, followed by a comma, then the number of decimal digits that we want to show for the results of that formula. All the reinforcement area parameters will have 2 decimal digits. As you can see here, for example, ASB, it is rounded to 2 decimal digits. All distances will be rounded to 2 decimal digits. Smaller numbers like reinforcement ratio and strains will be approximated to 5 decimal digits, where some parameters like C over dt and phi will be rounded to 3 decimal digits. By this, we complete the definition of all of our Excel formulas. I'm going to show them here and pause a little bit so that you can stop the video whenever you want at your convenience and copy these formulas to your Excel template. This here is the second part of it. Again, this table is the same as the table I have shown you previously, but I have introduced the round function to the formulas where it is necessary to have the round function. For example, d here is defined as h minus y bar, but the distance y bar here y bar has already been defined using a round function to 2 decimals, and thus when you are calculating d or dt, you don't have to use the round function because the number of digits display will depend on the outputs y bar and yb, which are defined here to have 2 decimal digits. I will pause on the rest of the equations here so that you can copy them at your convenience. Now you are ready to transfer all your formulas from Microsoft Word to Microsoft Excel. In my case, I'm just gonna copy and paste these formulas into their specified destinations, and what you can do is that you can just type the formula directly into the required destination. In my case, I'm gonna select everything here and click on copy, and then I'm gonna go to the Excel template, and here I'm gonna select paste while matching the destination formatting in order not to change the color of the cell. And now you are ready. This is the first output parameter, ASB. Let's do the same thing for the second one and paste using the destination formatting. The third one, paste, and so on. Now you can see that whenever you change the input parameters, the areas will change accordingly. Once you have completed copying all of your Excel formulas from the table that I've shown you earlier into your Excel template, then you will be ready to start testing different cross-sections for adequacy and design strengths. For example, the section with the input parameter shown here is inadequate, as the section fails because B minimum is greater than the actual width of the beam. The beam is incapable of encompassing the steel reinforcement placed in the layer farthest from the neutral axis, which is 6 bars of 16 millimeter diameter. Therefore, we can fix this situation by increasing the cross-section's width from 300 to 350. And the section will turn into tension controlled, and the design strength will be shown to the user. In the coming sessions, we will use conditional formatting to introduce different colors to the cells encompassing our output parameters, to indicate using colors that the section being analyzed is adequate or not. We will also link the results to a graph that will show the ductility status of the beam being tested, whether the beam is tension controlled or in the transition zone or in the compression controlled zone. Till then, best wishes.